Hello friends, welcome myself Vatsal Desai and today I will introduce you to the term semantic search. Nowadays semantic search is used heavily in different systems. Most of the people who are even using semantic search or who are either in the profession of AI, sometimes I find that even they are not well aware that what does semantic search actually mean. So I will today introduce you in detail about the semantic search with the code example as well. Now, as you see, this is how the Google search screen looks like, and whatever search you perform on Google search is actually a semantic search. I will explain how normally the search works. So once you type something, it is taken as a query, or you can say it is a search term or a string, whatever. So it is taken and it is embedded in the language which the algorithm understands, and at the same time, Google or any system behind the scene has a database which has kept all the documents again embedded in the same algorithm which the query or search string we have just embedded or encoded, and then those are matched, they are compared using certain metrics, and then whatever matches closely is that is prepared as a list, and then that is shown to the user. If needed, there is a re-ranking also done, like re-ranking means reorganization of the results. Like here in the screen you see that XYZ was the first one, but once you reorganize, ABC becomes the first, and then that is after being done, that is you are like an end user, you are shown the results on the screen. So what is semantic search? So ultimately semantic search means that the whatever search you perform does not remain strictly constrained by the spelling of the word. Instead, the contextual meaning of the word, like how the word has been used, and that is also considered, and based on that the results are provided to you. So let us say you want to, like you sometimes are feeling hungry and you want to search like what I want to eat, something like that. So you are searching something to eat, but you can't you may be figuring out like what I want to eat. So you type like I want to eat. So then it will suggest food items, not necessarily matching any specific spelling, but it will understand that if you want to eat, then there would be some food items to be matching. So it understands the context, and based on that provide the results. So that is what actually semantic search is all about. Now, why we are talking about semantic search now? So recently there has been enhancement in AI, like large language models, chat GPT, all are there, people are using them. So all of them have powered this semantic search extensively. So that is why we are right now discussing about semantic search. As behind the scene, these LLMs are the main power engine. Now I would introduce you basically to a terms text featureization. So I won't go into very technical detail, but when text is being used in machine learning algorithms, they are converted to numbers, and they are converted in a way that they do not completely lose their meaning, and still they are represented in the form of number. So there were different techniques which are known as text featureization technique. So primarily some of them which were used extensively earlier are like bag of words, then weighted word counts for that, TF-IDF, BM25, then later on as the neural networks usage started around 2012 or 13, there was a paper came, and that was around word2vec, where words were represented, started to be represented as vectors, and then at present we are using LLMs which are largely based on the transformer models. That is Vaswani's paper around 2017. So those algorithms behind the scene are used to create the text numeric representation of the text, which is ultimately a text featureization process. So text embedding. So what are text embeddings? So when you represent the words in a sentence, or the whole sentence or paragraph or the whole document in terms of vectors, then those are normally known as text embeddings. They are ultimately a relatively high dimension representation of those words in the embedding space, and they are, if you plot them in a two-dimensional space, you would see like you can plot them in a two-dimensional space. And this is a sample diagram taken from Wikipedia related to article related to word2vec glow, and in that you would see like words are placed in this way. For example, man, king are a bit closer, woman, queen are a bit closer. So that is how the meaning of words, a contextual meaning of words can be derived by the distance of these things, like these words. Now ultimately how semantic search is actually performed. So when you write a query, it is embedded as we have seen in the previous slide, and the relevant documents have also been embedded. Both have been embedded using a specific algorithm for text embedding, and then in the geometric space they are like placed something like this. So whichever document is close to the query is then returned. Now here if you see that the query is close by to only one document, this diagram has been taken from SBIRD website. But if you see, let us say the query has been on this leftmost side, then you would find three documents matching. Then if query would be here, then there will be multiple documents matching around the scene. So this is what is determined like by a value of k, like how many nearby documents we want to retrieve or we want to see to understand like what is the closest match. And the comparison is done using certain distance metrics like Euclidean distance, cosine similarity, dot product. These are some of the distance metrics which are being used. Now I will briefly show you the code as well. If you see in this notebook, we are importing certain packages like the SBIRD sentence transformer and the torch we are using for TopK. This is one of the model, bird page model, that is all mini LM L6B2, and this is our corpus, like you can call them as documents. So these are like different documents. A man is drinking water, a man is drinking a cup of tea, a woman is carrying a baby, a monkey is eating a banana, a tiger is climbing a tree. Let me change this tiger to something like wild cat. A wild cat is climbing a tree. Okay. Now, as I have explained, using this same algorithm, we are embedding this corpus and creating their vector representation. So this is their vector representation, and these are the query sentences. For example, now we would this is, for example, we have kept three sentences like a man is drinking coffee, someone in a gorilla costume is eating a banana, a tiger is near a tree to hunt a prey. Now here, as I have shown you that in the geometric space there are different candidates around that query document, and you would be able to understand like which document is closer using the distance. We are using the cosine similarity matrix here. It is a similarity matrix. So there are two things to be mindful. One is cosine distance and the other is cosine similarity. We are using cosine similarity here, which means that how close these two terms are, query and document. So as we run, you would see like the query, for query a man is drinking coffee, the closest match comes is a man is drinking cup of tea. Now a similarity score remains between 0 to 1 here. So highest is 1 value, means more similar or more close, and 0 means not at all similar. So 0.65 is a bit closer, like so coffee related sentence, a man is drinking coffee, is getting matched very closely with a man is drinking cup of tea. And then second match is a man is drinking water, maybe since it is also something which we can drink, but but the word coffee and tea might be more closer in the text embedding plot space, so that's why they have higher similarity. And you can understand normally, as we offer someone like you want to have a tea or a coffee normally, so that's how, so that type of meaning is being embedded in the embedding space, and that type of meaning is considered in the search, that's why it is called semantic search. Similarly, in this second example, someone in a gorilla costume is eating a banana, so we have not specified that we have mentioned gorilla, not a monkey or something like what is present in the corpus, but it was able to understand that monkey gorilla has like some sort of similarity, as we know. So first closest match is that a monkey is eating banana. Second is like it is not very close, you see the number 0.1145, so these are least matching, but we are finding like a top 5 to see like maybe something is matching closer by something like that. So that's what. And the third is a tiger is near a tree to hunt a prey. So here if you see, I mentioned a wild cat is climbing a tree, but as we know, wild cat and tiger would have more similarity, so that is what it has considered closely as a highest match. And then the monkey is eating banana and all, it might have matched some animal, but the distance, I mean the similarity is quite low. So everything else is like very far in the distance. Now I will briefly introduce you to key thing like cosine and dot product primarily. So in the earlier slide I mentioned that the different distance metrics are used to compare query and the document. So those three metrics which I mentioned in the earlier slide are Euclidean distance, cosine, similarity and dot product. Now these A and B in this diagram are vectors, and they represent the text of the query and document as far our example goes, where we want to compare both of them. So if you see in the Euclidean distance, they are merely the distance between both the vector is being considered, like how far the one vector is from the other. In cosine similarity, angle is considered, and in dot, angle is the key thing, and in dot product, this is one formula of the, you make them what you can say unit vector, and then dot product becomes equal to cosine similarity. I will explain you briefly in more detail this thing. So why normally cosine similarity is used to compare the vector. So as you see, this is the cosine curve plotted, and here you see that the value is between -1 and 1, where these are the angles. So at 0 and this is like both. If you see the other examples, for example, for most similar vectors, cosine, the theta value, for theta the cosine value would be 1, means both vectors are in the same direction, so they would be most similar. Between between both the vectors, if there is the angle of 30 degree, then it would be like a 0.86, so they have still a relatively good amount of similarity. And if they are like 90 degree angle, then the cosine of that angle is 0, so they have 0 similarity, and if it becomes minus, they are completely in opposite direction. So that is why these cosine between the vector, cosine angle between the vector is helpful in mapping the similarity, measuring the similarity between the vectors. And here both are the equation of cosine similarity and dot product. So this is the dot product equation. So if you see that the difference between dot product and cosine similarity, you would find that the numerator in the equation, both the equation is same, so this you can replace with the dot product, and these are like both vector. When we are dealing with two vectors, let us say A is a query, B is a document one. So if you normalize the vector, then into the unit vector, like it has been shown in the this diagram. So then as per the unit vector length of A and B, you would see that there won't be any denominator then, because it would be 1. So their individual vector value will become 1 as a magnitude of the vector. So its square root would also be 1. So it won't be so cosine cos theta for unit vector and the dot product would be equivalent. So this is the key thing. We are going to look through code as well to give you idea like when what is the benefit of using dot product in similarity measurement. So we'll go to the code. Okay, so this is the code. Now as you see, I have imported standard packages. This is NumPy, and this is the, from math we are using isClose to measure closeness of the normal closeness of the vector as per the precision value, not in the terms of angle. Here we are calculating cosine similarity. So this is like a dot product calculation, and then the individual vector norm which we are multiplying and dividing by it. This is a function to normalize a vector. So here I am generating some random vectors using NumPy random function with 1000 values, and then we are normalizing the vector. Now as you see that this is the normal vector value, and these are the normal, this is the normalized. So normalized value will be like once you normalize the vector, then its norm would be 1. Now if for both of these vector 1 and vector 2, when it is not normalized and we calculate cosine similarity, so this shows like it takes around 71 millisecond, sorry. And yeah, so here the dot product, the wall time for dot product calculation is lower compared to the cosine similarity calculation. So, and there is like more than a 50% difference between the calculation time between both of them. And if you see, the values are like, you can see that same values are there both. I mean, even at the later precision level also, I mean, that is what it is just trying to show. Now here I am downloading a book from the Gutenberg website, Project Gutenberg. I have already downloaded the book, so I am not re-downloading it. It is present like this, Hound of Baskerville. And this is the code to download the book. And then I am splitting the text into sentence and index. Just a minute. Here I will have to forward forgot to initialize the variable. So the book has been loaded in the text variable, and this is like briefly I am printing some sentences here. How did you know? And like the back of all this, there are some sentences from the book. Now, as I have shown you previously, we are embedding them. Some of the sentence we are considering them as a index and the other as a main vector. So we have divided the whole book, like the 5% part, and the rest 95% as index and search document. Like one would be query document in our consideration, and the other would be like the main corpus. So we are creating embedding here using the and here this normalize embeddings has been false, so we are not normalizing them. Means here we need to use ideally cosine similarity. These are like the vector values you would see. Okay, this is not important. So here we are doing a normalized normalization of the embedding and then downloading this. Now the key thing is here we are taking 200 records from both and comparing them. Like here if you see the cosine similarity comparison is going on, we are doing with search and index. So the wall time is around 4.66 seconds, and the same thing is done for dot product, and the time is 922 milliseconds. So this is a significant difference in the calculation speed. See, so when you are working for a different large size data set, so that is why using a dot product for similarity is a better idea. And if you might have used the embeddings like OpenAI, they are like normalized vectors, so they are already normalized, so you can out of the box use it for the dot product. And in different model embeddings are trained in a different way. So some of the embeddings are made in such way that they have been optimized or used for use of dot product. So there you can just directly use them without even normalizing them. Similar is the case with OpenAI embedding, and you would find even in the sentence bird site, some of the embeddings have like dot as a suffix mentioned behind, means the loss function and has been used in such way and they have been already normalized. So that is why it would be beneficial to use dot product in this way for the calculation efficiency. And I have shown you that results also do not differ as far as the similarity measurement is done. Thank you.